When AC flows through a coil, an alternating magnetic field is generated around the coil. Since the alternating magnetic field must cut through the turns of the coil, a counter EMF is induced in the coil which opposes the change in current flow. If the alternating magnetic field generated by one coil cuts through the turns of a second coil, an EMF will be induced in this second coil, just as an EMF is induced in the coil which is cut by its own magnetic field. This action is known as mutual induction.
The transferring of electrical energy from one circuit to another by means of a changing magnetic field is known as transformer action and is based on mutual induction.
A transformer is a device that transfers electrical energy. A simple transformer consists of two coils wound very close together but electrically insulated from each other. The coil to which the AC voltage source is applied is called the primary, identified with the capital letter P. It generates a varying magnetic field, which cuts through the turns of the other coil called the secondary, abbreviated as S, and induces a voltage in it. The coils are not physically or electrically connected to each other, but they are magnetically coupled to each other. Assuming that all the magnetic lines of force from the primary cut through all the turns of the secondary, the voltage induced in the secondary will depend on the turns ratio between the secondary winding and the primary winding. In this case, the secondary has twice as many turns as the primary. Voltage of the secondary divided by the voltage of the primary equals the number of turns in the secondary divided by the number of turns in the primary. For example, there are 10 turns on the primary and 20 turns on the secondary. If the primary voltage, E sub P, is 5 volts AC, what is the secondary voltage, E sub S? Solving for E sub S, the equation is E sub S equals N sub S divided by N sub P times E sub P. Substituting the values, E equals 20 turns divided by 10 turns multiplied by 5 volts. Therefore, voltage, E sub S, equals 10 volts. Since there are more turns in the secondary than in the primary, the output voltage is increased. This is known as a step-up transformer. The opposite is also true. If there are less turns in the secondary than in the primary, the output voltage would be reduced. In this example, the primary has 20 turns and the secondary has 10 turns. Solving the problem, you can see that the turns ratio is 1/2, 10 over 20, and that the secondary voltage, E sub S, is only 5 volts. Since there are less turns in the secondary than there are in the primary, the transformer is called a step-down transformer.
Remember, a transformer does not generate electrical power. It transfers electrical power from one coil to another by magnetic induction.
Since power equals voltage times current, then E sub P times I sub P represents primary power, and E sub S times I sub S represents the secondary power. Transformers are not 100% efficient, but are close enough for practical purposes. Therefore, the power output approximately equals the power input. E sub P times I sub P equals E sub S times I sub S. A step-up transformer produces an increase in voltage and a decrease in current. If the primary voltage, E sub P, is 10 volts and the secondary voltage, E sub S, 20 volts, then the primary current, I sub P, will be twice the value of the secondary current, I sub S. I sub P is 0.12 amperes. I sub S is 0.06 amperes. Conversely, a step-down transformer produces a decrease in voltage and an increase in current.
Transformers are classified as step-up or step-down only in relation to their voltages, not their currents. Since the voltages of a transformer are directly proportional to the turns ratio, the currents in a transformer are equal to the inverse of the turns ratio.
Transformers designed to operate on low frequencies have their coils wound on iron cores. Iron cores are constructed in two main types, core type and shell type. The core type offers a single iron path for the magnetic field to pass from the primary to the secondary, making an efficient transformer. The shell core provides two parallel magnetic paths for the magnetic field. This gives maximum coupling between the primary and secondary windings to obtain maximum efficiency. This is an actual power transformer using a shell core construction.
In actual practice, the secondary winding is first wound around the core, and then the primary winding is wound on top of the secondary winding. This provides for maximum magnetic coupling between coils. A transformer is not a perfect device, and some power is lost in the transfer of energy from primary to secondary. The energy loss is in the form of flux leakage, copper loss, and core loss.
Since the primary and secondary windings are wound with many turns of copper wire, the copper loss is the power consumed by the transformer current flowing through the windings. This power loss is in the form of heat and can be calculated by the I²R formula, where R is the coil resistance and I is the current through the coils. The varying magnetic field cuts the core, causing a current, called eddy current, to flow through the core. This eddy current heats the core and consumes power. If the resistance of the eddy current path is increased, less current will flow. Therefore, transformer cores are made using thin sheets of metal and insulated from one another with varnish.
Another core loss is called hysteresis. This loss is caused by the reversing of the magnetic polarity of the atoms of the core material.
The polarity of the atoms is indicated by the colors at each end. Each time the current reverses in the primary winding, the atoms of the core must also reverse their polarity, and frictional loss is developed.